Okay, so here's the first application. This is really the setting, and you know, I'm looking at something that is of importance here. This is these are the tracks of a. This is the track of Typhoon Fanapi. All right. What you see here in blue are the tracks of an airplane that flew in the hurricane track and threw into the surface of the ocean, actually threw in the top layer of the ocean, an instrument which we call AXBT, okay, Airborne Expendable Bathy Thermometer. This is an instrument that is shot in the surface of the ocean and is reporting the ocean temperature in the top layer, roughly the first 300 meters of the ocean, okay? So we were lucky that, you know, in this ITOP experiment, it was sold to, you know, the sponsors and the government, and, you know, that year there were no hurricanes, actually no typhoons. And these two typhoons came, and, you know, the people who are running this experiment jumped on the occasion and threw all the instrument that they had, because they had to use the instruments and report that they were used. So relatively speaking, we had quite a bit of the data as far as part of this experiment. Okay. All right. So as far as you know, my cartoon on the ocean, and I learned quite a bit from my friend Mo on how to model ocean. If we want to model the ocean, you can model the atmosphere without the ocean, but you really cannot model the ocean without the atmosphere, because it's really the surface winds that are a major part of the oceanic circulation. And relatively speaking, at least as far as this first part of the talk, we have fantastic, even though this is not true, but this is an exaggeration, we have fantastic ocean models, we have fantastic atmosphere models. I shall show you in a minute that this is not the case. But relatively speaking, where we're really not very good is at coupling them together. Okay? So quite a bit of the uncertainty looks in the drag parametrization. I'm running an ocean circulation only, and I'm driving it, you know, with its own internal dynamics and with the surface winds. Okay, and this is really the drag law that sits inside the ocean model. Okay, it has these expressions. You know, it has a temperature difference, which for hurricane conditions or typhoon conditions is not that important, but it basically says, if you give me the velocity, I will tell you what the drag coefficient is, and you know what this, therefore you can tell what the stress is, and therefore you know what the impact, or you know the stress that the atmosphere is applying on the ocean surface. Okay, these expressions has parameters, and I'll show you what they are. You know, the uncertain parameters are alpha, V max, and M. And if I remember my own slide, here's where they are. I really hate the slide. Okay, I mean, I hate it for many different reasons. I really need to apologize for, but it really is what it is. And the sin that the slide is making is that on the x-axis, I have a velocity which has dimensions, okay, which is in meters per second. And on the vertical axis, I have a dimensionless quantity. Okay, I spend, you know, half my time telling my students never ever do that. But it is what it is. Okay, this is how the observations were reported. You know, you should not do that, but this is so ingrained that I really must start with an apology. The other thing that I don't like about it, but it's a fact of life, is that the experimental conditions, which come from a whole lot of things that I suppressed, but they are in the paper, they come from lab experiments, drop zones, other things, they're really all over the place. And the three parameters that we're uncertain of are the slope, okay, of the data, where it saturates, okay, and whether the data beyond the saturation remain flat or actually drop at a certain slope which is given by M, Okay, and why it makes sense? Okay, so you start the wind start increasing. You know, when wind increase, you know, waves develop. With wave, you have increasing roughness, so it really makes sense that this thing increases beginning. When the wind is very strong, okay, then the waves are actually being sheared off, and we really don't know much in that condition what really takes place. Some theory says that the drag coefficients remain flat. Others say that it actually starts decreasing, and there is really uncertainty in that. And we wanted to see whether the data that is collected by the ITOP experiment could inform us on some of these. The pink curve is what actually goes in the operational in the operational model, and the uncertainty is uncertainty around that. The operational model that we're using is what the US Navy uses. This is the HICOM model. Okay. Before we run into uncertainty, I told you the ocean, the atmosphere was perfect, where it's really not perfect. Okay, what I'm showing here is on the x-axis is time, on the y-axis is wind speed for two typhoons, you know, Fanapi and Malakas. Fanapi is the one I'm focusing on, all right? And the other one I'm showing tracks, all right? So this is the, you know, if I want to take Fanapi, this is the red curve, JTWC, this is the Joint Typhoon Warning Center. This is observational data. The blue is our prediction, okay? And, you know, when we're running the weather research and forecasting model you're reading it correctly, 1.3 kilometers. And 1.3 kilometers is a little bit quite insane. I'm really not a numerical weather person, but this is much finer than you would actually need in a very good, you know, weather prediction or weather forecast, okay? And if we're looking at the tracks, then we're also doing very well. Okay, so you know, the tracks are there. The reason we wanted to get to this resolution level, okay, this is a little bit showing you our dirty laundry, or what's really under the hood. If you run WRF at 12, 4, and 1.3 kilometers, and between 12 and 4 is where actual weather prediction, the resolution that actual weather prediction takes place. These are the tracks that you see. Okay, so you started with 12, and we said, come on, we said to our you know, weather colleagues that, come on, we really cannot start inferring parameters if the tracks of the hurricane is in the wrong place. So can you help us out a little bit? So they said, oh, you're nice guys, we're going to run WRF at 4 kilometers. Well, you run it at 4 kilometers, it went worse. Before they dropped it to 1.3, and at least we had the hurricane, or I should say the typhoon. We had the typhoon in the right place with the right wind intensity. Otherwise, if you simply run your inference exercise, all I'm inferring is essentially hallucination, because if the typhoon is really not in the right place, this is entirely prediction error, and this is what I'm calibrating, right? So there is quite a bit of heavy lifting for the setting to be correct, and we did that. And once we did that, then the observation, okay, which is on the vertical axis, versus the simulation, both at, you know, early enough and at several days later, these are beyond the initial conditions. Nothing is really assimilated in these runs. Okay, then we could get the data and the observation on the same. In the same ballpark. They're telling us essentially you're in the same field, and we're exploring, you know, this pretty good agreement between the two to see if we can refine the priors on these three parameters: the initial slope, where it saturates, and what it does after the saturation. Okay, I'm applying Bayes' rule after I build my model surrogate. So when I'm running the Markov chain Monte Carlo, what I'm pulling is the functional representation, or the PC expansion, or the emulator. I'm not pulling new. So I really need to, here my uncertainty is every possible value of alpha, V, Vmax, and M. And I'm doing it not by running a new model, but by sampling the surrogate instead of the model itself. And I need tens of thousands in order to get convergence, and in order to to get my posterior. Okay, in this simple case, this simple likelihood function turns out to be sufficient. Okay, so I have my model, I have the observation, I have a nuisance parameter, and I'm trying to infer all of these through my Markov chain Monte Carlo procedure. Okay, you know, Markov chain Monte Carlo gives me chains. The chains look pretty nice. And I'm not looking only at the chains themselves, but I'm looking at the chains and the nuisance parameters that are associated with each. And I use essentially the converged distribution to look at, in this case, marginal posteriors. Okay. Obviously, the marginal posteriors are embedded in here, but this is also a slide that, you know, for the purpose of this presentation is nice. But if you actually take the trouble of run Markov chain Monte Carlo, please tell me something about the full posterior, okay, instead of just doing what I did in here, which is show you the marginal posteriors, okay? So if you have the full posterior, it's really a catastrophe if you just project it onto marginals, because there is quite a bit in the correlation structure that can be informative, and we don't want to I don't mind throwing data away, but I mind throwing information away. All right. So if we look at what we use for the maximum velocity, this is the prior that I have. Theories told me essentially that it could be anywhere between 20 meters per second and 35 meters per second, and we get a relatively sharp posterior. You know, not at the edge, but you know, close to the edge of our prior. But the distribution is actually quite sharp. All right, for the slope, okay, which we postulated to vary between 0.9 and 1.1. 1 is the value that is actually used in the operational forecast. We get something that is very sharply peaked, okay? So in order to be consistent with the AXBD data, we cannot tolerate slopes that are outside this range. And as far as the slope beyond the saturation, okay, the data is simply not informative at all. And the reason it is really not informative is that we, relatively compared to to where we got observations, unfortunately, the hurricanes really did not fly into the 100 meters per second wind. And this is really what we wanted to do next time around if they have the courage to do that, but we simply did not have sufficiently enough data at those very high wind speeds to be able to inform, at least with temperature measurements, and what happens in that. So there is really, if we really run into these situations unfrequently, there is little I can tell you whether the drag coefficient is actually dropping or staying flat, because it really doesn't matter that much as far as these observations are concerned. Okay? And this is really what the push forward posterior for this maximum a priori values looks like. It's quite a bit close to the values that are used in the operational models, which is actually quite reassuring that the operational models are actually using the right things. All right. Obviously, what we can do with Markov chain Monte Carlo, we can also do through a variational setting, and this is really what I attempt to make the link with variational approaches and Kalman filtering type ideas. If I use this likelihood function, so this is what I'm interested is the posterior of my parameters and the nuisance parameter given the data, right? And if I express it into this way, assuming my prior to remain flat, which is really simplifies life, taking the logarithm, this is what I have. So this is the log likelihood, all right, of that. And you know, if I have a functional representation of my model, okay, then I can form the adjoint, not only the adjoint but the Hessian of this quantity, okay. And then I can try to minimize the distance using this adjoint and this Hessian, right? So, oops, I'm trying to point right? So in a variational type approach, what we're trying to do is looking at the parameter vector theta that maximizes the likelihood or the log likelihood. And the way I go about it is through a variational approach. I try to maximize it, okay? But because I know the Hessian, both the adjoint and the Hessian, or the Jacobian and the Hessian, this is something that I can do rather easily. And remember, the reason I can do that is because I have a functional representation of what my model is in terms of the parameters theta, okay? Differentiating it with respect to the nuisance parameter is also quite immediate. Okay, so what we're actually trying to do is trying to minimize this cost functional, and given the observations and where it works out, okay, this is really what you have in terms of an adjoint. If you had an adjoint model, or which really comes about in an assimilation setting quite frequently, in this particular case, where this is really being enriched by other terms, which comes from nuisance parameters, and the Hessian is something that I can also form, again, because I have functional representation of the impact of the impact of the uncertain parameters on the model, and therefore on the quantity of interest, and therefore on the cost function. Okay. So I can start with any point and run my adjoint machinery. So I start in here, and then I have